Welcome. Today I'm going to talk to you guys about universal gravitation. In my world right now, the new Star Wars movie just came out, so everybody's talking about the force that binds the galaxy together. And for physicists, when you start talking about forces that bind things together, we talk about gravitation. So it kind of is appropriate that we talk about this right now. It just so happens that our basic understanding of gravitation really comes from Isaac Newton back in the 1670s. In addition to doing cool things like developing our laws of motion, revolutionizing our understanding of optics, inventing a whole new branch of mathematics called calculus, he also came up with a way of describing how the universe stays together, and specifically how the objects in the solar system stay in their orbits. And to explain it, he came up with this idea called universal gravitation. Now, universal, of course, means that it happens not only throughout any location, but also between any two objects. And so we want to keep that in mind, that universal really means not only does it happen on Earth, but it happens anywhere, and it happens between any two objects that you could have. And then gravitation, we talked about that before. It's actually one of the four fundamental forces in the universe. It's weird because it's one of the forces that only has an attractive side. It doesn't have a repulsive side, like electromagnetism. Electromagnetism, you could be repulsed by an electromagnetic force, just like you'd be attracted by an electromagnetic force. Anyway, so here we have two objects. They could be a planet and a moon. They could be a large sphere and a small sphere. It doesn't really matter. We should find that there is some gravitational force that exists between both. That gravitational force is pulling them together, and it affects both of them, right? So this blue sphere is being pulled slightly by the red sphere, but we also find that the red sphere is being pulled by the blue sphere. And so as a result, they each have forces that are acting in towards their center. Now this makes sense, right? Because remember, Newton's third law says for every force there's an equal but opposite reaction force. And in our class we talked about the fact that you could take the sentence and then flip the subject and object, and it would work just as well to help to describe Newton's third law of motion. So the blue sphere pulls on the red sphere with a gravitational force. Newton's third law says flip them. The red sphere pulls on the blue sphere with a gravitational force. And so it works either way. And so we know they must feel the same force. So right now I'm being pulled downward by the Earth by a force of about 750 newtons. How much am I pulling up on the Earth? I'm pulling up on the Earth by a force of about 750 newtons. That's how gravity works, in addition to Newton's third law. Now, as I was talking about with the force, I have a little superhero, or a Jedi right here, who's trying to attract this rock over to him. Now keep in mind that this would probably not work very well if you were an actual Jedi or superhero, because the force that you would apply to the rock would also be applied back to you. And we know from Newton's second law, if you have a force applied to you, your mass determines how much acceleration you feel. And so this probably has a lot more mass than the superhero. And so as a result, the superhero would probably go flying towards the rock rather than the rock come flying towards him. So there's a little what we call willing suspension of disbelief in some of those superhero stories, comic books, and of course in Star Wars, unfortunately. So there you go. Okay, so what does the law of universal gravitation look like? Well, I think it's astounding that first off, that Newton was able to come up with this all in his head based off of logic, not off of experimentation. I think it's amazing. Now, he didn't come up with necessarily all of it. He came up with the formula, but the details were filled in by other people later on, namely Henry Cavendish, who did all sorts of cool stuff, but not as cool quite as Newton. So let's take a look at it here. Here it is. The gravitational force is what's listed on the left-hand side, F sub g. We have talked about that quite a bit. We've used that as a synonym for weight. And as you know, when you're talking about the Earth, that's okay. We can talk about F sub g as weight. But in this case, we're talking about any gravitational force between any two objects. It doesn't really matter. So the g right there means gravitational, not just the weight in this case. So the weight, the gravitational force is equal to the mass of the first object times the mass of the second object divided by the distance between them squared. Now all of that has to be multiplied by a constant, which helps us to convert the units into newtons so that we have an actual force over here. Because you can see we have kilograms times kilograms divided by meters squared, which kilograms squared divided by meters squared, that's not what a newton is, so we need to fix that to make sure that it works. The problem is that that big G right there, sorry, is actually quite a small number, which is why I stumbled over my words right there. Big G is actually very, very small, and so you'll see that in a minute here. So let's take the situation we had before. Let's say this blue sphere has a mass of 2 kilograms, the red sphere has a mass of 1 kilogram. And so what's the gravitational force between them? Let's say the distance between them is 1 meter. We're just going to try to keep the math as simple as we possibly can here. So let's say that's 1 meter, just so you guys can see how this works. I want to be able to, as much as possible, do the math in my head. So we'll see how it goes. Okay, so this big G right there has a special value, as I told you just a minute ago. Big G is not at all 9.81. It's not. Big G, little g, they're totally different things. Don't confuse them. So big G is actually 6.67 times 10 to the negative 11th. I told you it was small, right? Negative 11th, that's really small. That's very, very, very close to 0. That's to try to fix the units there, right? So 6.67 times 10 to the negative 11th. Okay, makes sense. And then the units are newtons times meters squared over kilograms squared. So the meters squared cancels out those units, the kilograms squared cancels out those units, and then we're left with newtons left. So that's all we have. So how much force is between these two spheres? Now, I want you to think about this. Let's just get a gut reaction here. If you have a 2 kilogram mass and a 1 kilogram mass and they're 1 meter apart, do you notice them flying together all the time? Because these are like everyday objects, and this is an everyday distance. So do you see things flying together gravitationally all the time? No, you don't. So you can imagine that the force that you're going to see is very, very, very small. And in fact, you should also notice that 10 to the negative 11th means it's going to be extremely small. It's going to be on that order, 10 to the negative 11th newtons right there. So let's see what we got. What's the gravitational force between them? So we go 6.67 times 10 to the negative 11th times the mass of the first mass right there is 2 times the second mass, which is 1, all over the distance squared. Okay, so what do we get? What do we get when we take this now? You can see here that 2 times 1 divided by 1 is just going to be 2. So we're just doubling this number right here. So because I want to make sure that I'm right here, I'm going to go ahead and do this on my calculator. Now, this brings up a good point. When you do work with scientific notation on your calculator, you really should use a special button called EE, the EE button. And that EE button actually takes the times 10 to the, and then replaces it with an E. So this actually becomes something that looks like this, 6.67 E negative 11. Now the cool thing about that is your calculator thinks that's one number. The E links these two things together. This, the calculator thinks are two different numbers. So 6.67 is one thing, 10 to the negative 11th is a different thing. Here, if you use that, it's one thing. And that actually comes up quite a bit. It makes your life a lot easier if you can get into the habit of using that. And that's all times 2. So I'm just going to go ahead and do that here. 6.67 EE. I got to fix my stupid iPhone here. 6.67 EE negative 11. And then times 2. Okay. So I get, let's see, 4, 5, 6, 7, 8, 9, 10. 1.334 times 10 to the negative 10th. So I'm going to go ahead and erase that so you don't get confused. F sub g equals 1.334 times 10 to the negative 10th newtons. Now 10 to the negative 10th newtons is very, very, very small. Remember, I weigh about 750 newtons. An apple is about 1 newton. So we're talking about it would take the force of 10 to the 10th of these to be able to equal the weight of 1 apple. So we're talking about 10 to the 10th. That's like what, 10 billion? So 10 billion apples. Sorry, 10 billion of these would equal the weight of one apple. So that's very small, you can see, and that's why we don't notice things moving together. However, if you put them in a vacuum, in a perfect situation, and then you sent them off into space where they could just float there forever in a vacuum with no air resistance and no gravitational fields that they were dealing with, just floating, you would find, if you waited long enough, that they would begin to move, visibly begin to move towards each other. It would take you a long, long time to notice it. I mean, probably billions of years to notice it, but you could, because that gravitational force is a net force and it does cause an acceleration, even though it's a very, very small acceleration. Thanks for watching.